Have you ever stopped to think about the world around you? Not just the big things like the sun rising or the seasons changing, but the small details. The patterns you see every single day. Think about a simple honeycomb with its perfect repeating hexagons, or the delicate six-pointed shape of a single snowflake landing on your sleeve. These aren't just pretty designs, they are clues. They are hints that our universe follows a set of rules. Deep, fundamental rules that govern everything from the smallest particles to the largest galaxies. These rules are often expressed through the language of symmetry, a concept that feels familiar and yet holds profound secrets. Symmetry is all around us, a constant and reassuring presence in our lives. We see it in our own reflection in the mirror, a near-perfect copy of ourselves. We find it in the balanced design of a butterfly's wings, each side a mirror image of the other. This idea of balance, of one part matching another, is something we instinctively understand and appreciate. It suggests order, stability, and a kind of underlying logic to the way things are put together. But what if I told you that this simple idea of symmetry is one of the most powerful tools we have to understand the very fabric of reality? It's the key that unlocks the deepest mysteries of the cosmos. This journey we're about to take isn't just about admiring beautiful patterns. It's about looking beneath the surface. We're going to explore how scientists, particularly physicists, use the concept of symmetry to build their theories. They don't just see a pretty shape. They see a mathematical principle at work. Symmetry, in its most basic form, is about transformation. It's the idea that you can do something to an object, like rotate it or reflect it. Take a perfect square, for instance. You can rotate it by 90 degrees and it remains unchanged. You can rotate it again by 180 or 270 degrees and it still looks like the same square. This principle extends far beyond simple geometric shapes. Nature is absolutely filled with these kinds of symmetries. Look at a starfish. Most have 5 arms arranged around a central point. You can rotate a starfish by 1/5 of a full circle and it will align perfectly with its original position. This is called rotational symmetry. Or consider the intricate branching patterns of a fern leaf, where smaller parts of the leaf look like miniature versions of the whole. But physicists take this idea one step further. They ask a powerful question. What if the laws of physics themselves possess a symmetry? What if we could perform a transformation not on an object, but on our entire experiment, and find that the underlying laws governing it remain exactly the same? This is the leap from the symmetry of things to the symmetry of principles, and it's where our story truly begins to unfold. Imagine you are conducting an experiment in a laboratory. Let's say you are measuring how a ball falls under gravity. You measure the time it takes to hit the floor. Now, what if you picked up your entire lab and moved it 10 meters to the left? Of course not. The outcome of your experiment would be identical. Similarly, if you waited an hour and performed the exact same experiment again, you would get the same result. The laws of physics don't care where you are. This is a profound type of symmetry. A fundamental quantity is conserved. In this case, the symmetry of space leads directly to the law of conservation of momentum, and the symmetry of time leads to the law of conservation of energy. These are two of the most important principles in all of science, and they arise directly from symmetry. It was formulated by the brilliant mathematician Emmy Noether in the early 20th century, and it completely changed how we think about the world. Right, so far we've been dealing with what physicists call global symmetries. This is the idea that when you perform a transformation, you have to do it to the entire universe all at once. Like when we moved our entire laboratory 10 meters to the left, we moved everything. The ball, imagine you're standing in a vast field of wheat, stretching to the horizon. A global change would be if the wind blew from the north, causing every single stalk of wheat to lean in the same direction, at the same angle, at the exact same time. A playful gust of wind swirls through the field. Imagine our universe has a rule that every person must face a certain direction, let's say north. To maintain the symmetry, if one person turns to face east, everyone else in the entire universe must also turn to face east at the exact same moment. This is a very restrictive system. We want the freedom for each person to choose which direction they face, independently of everyone else. At first glance, this is complete chaos. But what if there was a way to connect everyone's choices? Imagine we invent a set of instructions. This is the big reveal, the central idea of gauge symmetry. When you demand that a physical law has a local symmetry, that you can make a change at one point without making the same change everywhere else, you are unavoidably forced to introduce a new field. This field is not optional, it is a logical necessity. Its job is to be the messenger, the connector. It exists solely to ensure that the laws of physics look the same for every observer. Let's take a closer look at our first and most familiar example, electromagnetism. This is the force responsible for almost everything we experience in our daily lives. It's the light from the sun. The particle at the heart of this is the electron. This messenger is the photon. This theory, which marries quantum mechanics, special relativity, and gauge symmetry, is called quantum electrodynamics, or QED. First, there's the strong nuclear force. This is the most powerful force we know of. Physicists proposed a new kind of charge for quarks. These are the gluons. Then there's the weak nuclear force. These were named the W+, W-, and Z bosons. In 1983, at the CERN laboratory in Geneva, physicists smashed particles together at enormous energies. Now, let's put all the pieces together. We have three fundamental forces, each described beautifully by its own local gauge symmetry. This grand structure is known as the standard model of particle physics. It is our best, most tested description of the fundamental building blocks of the universe, is dictated by the mathematical group U, 1 times SU 2 times SU 3. But you can think of it as the master blueprint for reality. This model has been spectacularly successful. Like the Large Hadron Collider at CERN, the most famous of these is the Large Hadron Collider, or LHC at CERN. It's the largest and most powerful particle accelerator ever built, to accelerate protons to almost the speed of light and smash them together with incredible violence. Like Atlas is to meticulously track every particle to see if it matches the predictions. Every single collision is a test of gauge symmetry. For all its incredible success, we know the standard model is not the final word, but it leaves some of the biggest questions in science completely unanswered. For instance, the standard model has nothing to say about gravity. A primary goal of modern theoretical physics is to find a grand unified theory, or GUT. Furthermore, the standard model cannot explain the existence of dark matter and dark energy, makes up only about 5%. The vast majority is some mysterious, invisible substance called dark matter. These unanswered questions are not failures of gauge theory, they are invitations. What is truly remarkable about this story is how it has completely flipped our perspective on how science is done. For centuries, physics was largely an observational science. We saw something happen, an apple falling. It suggests that we can begin with a purely aesthetic and mathematical principle. It allows us to predict the existence of forces and particles, and it is where gauge symmetry has triumphed beyond all expectation. And it guided the decades-long search for the Higgs boson. So the next time you look at your reflection in a mirror or admire the balanced wings of a butterfly, I hope you'll think of this story. I hope you'll see beyond the surface pattern. The universe is filled with rules. They are more like the elegant, generative rules of grammar. They are rules that create possibilities, that give rise to the complexity and richness we see all around us, the forces that shape our world. They are the servants of symmetry. This is a vision of the universe. It suggests that everything we see, the quest of science, is to uncover these hidden rules, is the language of symmetry. Our journey through the world of particles and forces, the search for knowledge is far from over. It reminds us that sometimes the key to understanding the grandest, most complex phenomena in the universe can be found by contemplating the simplest and most beautiful patterns right here on Earth. The rules are hidden, but they are there, waiting for us to find them.